Hello everybody. So, till now we have gone through, or rather we have discussed several aspects of the first and second law, and based on these two laws we found out we have developed these particular we have developed these particular equations in this particular case. So, the things which we have the different equations that we have defined, the first equation was this, and the second equation based on the first law this was the equation, based on second law this was the equation. Now, if you observe these equations, we found that as a consequence of the first and second law we have defined two new properties. First law defines du and the second law defines ds. And if you observe closely, you will find that both these properties have been defined as differences and not as absolute values, which implies, rather from this we find that all the other equations that we have suggested, for example, the different criteria of spontaneity that we have selected, you find that all of these they are defined in the terms of difference quantities. And let me tell you, this is the greatest, or rather this makes phase equilibrium thermodynamics much more difficult. Why? Because since we define all the properties as difference properties, so as a result of which the specification or the definition of standard states become very difficult, and therefore, and it is also very important that when you have a big equation, or rather when you have an equation comprising of different properties, it is important to ensure that the standard states for all the properties are taken, or they are the same. So, these particular small aspects, as we shall see while proceeding towards the succeeding classes, we will see these are the things which make this subject slightly more difficult, and it is very important that a student concentrates on these aspects when he is dealing with this particular subject. So, based on the equations, we find that these are the different criteria of spontaneity for different interactions between a system and a surrounding. Now, let me remind you once more that we have done this only for assuming that we are dealing with just PV type of work. All of us know for isolated system it's the entropy maximization principle, and which gives us the energy minimization principle and the enthalpy minimization principle for constant S and V and S and P. Now, before I proceed, I would just like to ask you one thing. If you look at this particular equation, what does it show? It shows that for a spontaneous process, the energy has to keep on decreasing. Does it mean that the spontaneous process will only proceed when the energy of a system keeps on decreasing, or does it mean that energy of the system has to keep on decreasing for a spontaneous process and finally the energy will, or the system will sink into a zero energy sort of a sink? It is not that. This particular statement is basically a disguised statement about entropy. This basically means that for a constant entropy process, if a process has to be spontaneous and it is occurring under constant entropic conditions, then the internal energy has to decrease at the expense of energy moving from the system to the surroundings. Or in other words, it means that if the entropy of a system is maintained constant, then in that case heat has to flow, or rather energy has to flow from the system to the surroundings for a spontaneous process to occur. So, this is in reality a disguised statement about entropy. And from these two, in the last class we had defined that for constant volume and temperature conditions, it is the Helmholtz free energy which is important. For constant pressure and temperature conditions, it is the Gibbs free energy which is important. And it is important for you to know that usually in your practical applications, we deal with constant temperature and pressure conditions, and therefore Gibbs free energy you will find that is going to be our companion throughout this particular course on phase equilibrium thermodynamics, it is also important for reaction equilibrium. Now, after this, what do we get? So, from there, what does it imply? It implies that it implies from this particular equation, it implies that more or less we find out that from this particular equation we find out that suppose we are plotting, say G, suppose a spontaneous reaction occurs, and in that particular spontaneous reaction we are plotting the Gibbs free energy versus time. What do we observe? We observe that initially the Gibbs free energy, it keeps on decreasing, right. This is the time where the spontaneous reaction is occurring, and after a while when equilibrium has achieved, then we find that dG becomes equal to 0, and this signifies the equilibrium condition. For this particular case it was dG less than 0, for this particular case it is dG equal to 0. Same way, if you would like to plot the Helmholtz free energy as a function of time for a constant volume and a constant temperature conditions, we find that while the spontaneous reaction is occurring, the Helmholtz free energy keeps on decreasing, and finally when equilibrium has achieved, dA becomes equal to 0, right. So, therefore, if you observe, suppose at constant temperature and pressure, Gibbs free energy, I have said this is equal to G minus Ts. So, at constant temperature, suppose we would like to plot, or rather we would like to find the change in Gibbs free energy when the process occurs. This can very well be written down the way I have written it down, delta G equals to delta S minus T delta S. From here, what is the first thing that you observe? You observe that enthalpy dominates at low temperature and entropy dominates at high temperature, right. So, therefore, when we know that a spontaneous process has to occur, for that particular condition delta G is less than 0. How can delta G be less than 0? When delta H is less than 0 and delta S is greater than 0. We know that for such a situation, the process, it is a feasible process, or in other words, the process is spontaneous. Again, suppose we find that for any particular equation, delta H is greater than 0 and delta S is, say, less than 0. Sorry, here I have made a mistake, it should have been delta S greater than 0. So, for this particular situation, we definitely know that for this situation delta G will be greater than 0. As a result, this process is not feasible, but it will be feasible in the reverse direction, right. The problem starts when delta H and delta S, they have the same sign, which means that both of them are positive or both of them are negative. Under that condition, the change in Gibbs free energy represents a compromise of the system's tendency to decrease enthalpy and increase entropy under constant temperature and pressure conditions. Let us take a definite example in this particular aspect. Suppose we take a definite example here, what do we find? We find that the very typical example of, say, ammonia and HCl reacting to find NH4Cl. We know that for this particular reaction, the heat of reaction is known to us, as well as the delta SR is known to us. Both of them are negative. Just if you observe the entropy change of this particular reaction, what will you get? You are going to find that the entropy change, it is negative. Just if you are not aware enough, it will immediately appear to you that this reaction should not occur in the forward direction, but the reverse reaction is possible. But in order to find this out, since in this particular reaction occurs under constant temperature and constant pressure conditions, it is important to find out delta Gr at the same conditions of 1 bar pressure and 298.15 Kelvin. It is not difficult, you can just find it out by plotting, rather by calculating delta Hr minus 298.15 into delta Sr. What is the value that you get under this condition? We find that the value is minus 91.2 kilojoules per mole under this condition. Immediately from the value of delta Gr, you know that this reaction is spontaneous, which is the actual case under normal circumstances. Same way, suppose I take another very common example, vaporization of water. Although this is a physical process, I have denoted it in the form of a reaction. We know the standard enthalpy of vaporization and the entropy of vaporization of water at 1 atmospheric pressure around 100 degrees centigrade. Let us calculate delta G vaporization at 1 atmosphere pressure and exactly at 100 degrees centigrade, that is 73 degree Kelvin. Just calculate it and you are going to find that this will almost be equal to 0. Now, repeat the calculation for 1 atmosphere pressure and say 363 degree Kelvin or 90 degree centigrade. Just calculate it and you are going to find that it is going to be plus 1.10 kilojoules per mole. And suppose you calculate this for 383 degree Kelvin, what do you find? You find this is about this is around minus 1.08 kilojoules per mole. So, immediately from these particular values of delta G vaporization, immediately you have got the answer that why water vaporizes at 100 degree centigrade and steam condenses at 100 degree centigrade. Since delta G vaporization is almost 0 at that temperature, therefore, this process at 100 degree centigrade is reversible and it is feasible in both directions. And this also gives you the answer that why your condensation of steam to water is spontaneous at 363 degree Kelvin, because delta G vaporization is positive. So, naturally the reverse reaction is spontaneous, and at 383 degree Kelvin we find that the reaction, it is spontaneous in the forward direction. So, therefore, just by calculating the delta G vaporization values, we know that the reaction can occur in both ways for 100 degree centigrade, and this particular direction, it is spontaneous for 383 degree Kelvin, and this particular reaction is spontaneous for 363 degree Kelvin. We can take up several other examples as well, but anyhow these are the two typical examples which I have shown, so that you can appreciate the importance of appreciate the importance of calculating delta G vaporization. Well, so far as I have already mentioned that we have just considered a closed system with just PV type of work. This I have been repeatedly mentioning you. What happens if suppose there is some amount of non-PV work also performed by this particular system, any particular closed system. Let the system be closed, but it performs some non-PV type of work. Naturally, along with PdV, then what do we have? Along with PdV, then we have one FDR term as well, isn't it? Where F is the thermodynamic driving force and R is the thermodynamic displacement. Under this condition, do the same criteria of spontaneity hold? For constant S and V, what was the criteria of spontaneity? The criteria of spontaneity was dV less than equal to 0. Do you expect the same criteria to hold in this particular case? No. If you just substitute the equations at constant S and V, you find that the criteria du SV less than equal to 0 does not hold for constant S and V conditions. On the contrary, what should happen under this particular condition? Under this particular condition, we find that du plus dw non PV, this particular term should be less than 0. In the same way, for constant S and P, what should be the conditions of spontaneity? It should be dH plus dw non PV is less than equal to 0. Same way, if we continue, we find that for constant volume temperature conditions, this is the equation, and for constant pressure temperature conditions, this is going to be the equations. So, therefore, from here, what are the things that we have found out? We have found out that when there is some amount of non PV type of work, under that condition, we find that whenever there is some non PV type of work, under that condition, the amount of useful work or the non PV work that we can get from a system, or that has to be performed on a system when it moves from one equilibrium state to another, is equal to the decrease in, these are all, the decrease in the internal energy of the system at constant entropy volume conditions. If the process occurs under constant entropy pressure conditions, then it is the decrease in the of the enthalpy, and usually what we find the reactions occurring or the processes occurring for constant temperature volume or constant temperature pressure conditions, and under these conditions we find that the amount of non PV work that can be obtained from a system is equal to the decrease in the Helmholtz free energy or the Gibbs free energy of the system. Again, I would like to remind you that since we are mostly concerned or interested with constant temperature pressure conditions, so therefore, dGTP is going to be of interest to us, right. So, therefore, for non PV type of work, we find that more or less, well, so from the last slide, let me just write down this equation once more. What does this equation show? This is the equation which I had derived in the last slide, right. Now, from this particular equation, if you observe this equation, we can write it in two particular ways. The first thing is, we can write it down as dGTP is greater than equal to minus dW non PV. What is minus dW non PV? If you remember the sign convention which we are using, this is Q in is positive and the Q out, that is negative. Work done by the system is positive, work done on the system is negative. So, therefore, minus dW non PV is the work done on the system. So, we find out that the work which has to be done on the system in order to bring, or rather to effect some amount of change in the Gibbs free energy, it is for a reversible process, we find that dGTP equals to minus dW non PV, and we find that for an irreversible process, we find that the useful work which is done on the system is minimum for the reversible process. So, from these two things, what do we deduce? We deduce that useful work done on system, it is minimum for, it is maximum for useful work done on the system, it is minimum for reversible process. And similarly, we can also write it down in this particular case, if a system has to perform work on the surroundings, then that has to be accompanied by a decrease in the Gibbs free energy. We find that the decrease in the Gibbs free energy is equal to the non-PV work for reversible process, and this is less than the non-PV work for the irreversible process. So, from here what do we find? We find that the useful work obtained from a system, useful work obtained from system, that is maximum for reversible process, right. So, therefore, what can we deduce from here? We can write the equation in two particular modes. One is one shows that the decrease in Gibbs free energy is equal to the useful work done by the system, and we find that the maximum work that can be extracted from the system is obtained for reversible process, and whatever useful work we can obtain for the system for an irreversible process is less than the useful work that can be obtained for a reversible process. In the same way, if we have to perform work on the system, then we find that the minimum work that has to be done on a system in order to effect some particular change in the Gibbs free energy, that is minimum for a reversible process. For any particular irreversible process, the work which we have to perform will be much greater in that particular case. Or in a nutshell, suppose we would like to tell this in a nutshell. So, therefore, we can say it as that the work done by a system is either less than or equal to the decrease in Gibbs free energy for constant temperature and pressure conditions, for example, in an exothermic process, and the work done on the system is either greater than or equal to the increase in Gibbs free energy for constant temperature and pressure, for example, in an endothermic process. It is important to remember that this is applicable only to a closed system. Now, when we relate these particular terms with the useful work which can be obtained from a system or useful work done on this system, does this tell you or does this suggest any particular similarity with any term which you had studied earlier? If you recall, you find that in mechanics a potential AR was defined as AR2 minus AR1, and that was equal to the work needed to go from R1 to R2. If you remember this thing, so therefore, in mechanics a potential was defined as the work needed to go from R1 to R2, and that was equal to the difference AR2 minus AR1. The decisive point in this particular case was that AR, it did not depend on the particular way which was chosen to go from 1 to 2, as long as the acting forces were given as the derivative of the potential with respect to the coordinates. If you compare, we find that in this case also U, H, A and G, their differences give us a measure of the amount of work needed from going from state 1 to 2, and they are independent on the particular way that we have chosen in going from 1 to 2. So, therefore, by analogy with mechanics, all these four terms can be termed as thermodynamic potentials, and they can be related to the work or rather the useful work attained or performed on a system for different coupling of the system and surroundings. I repeat, du gives you the non-PV or the amount of useful work that can be obtained under constant entropy volume conditions, H for constant entropy pressure conditions, A for constant temperature volume conditions, and G for constant temperature and pressure conditions. From here, therefore, in a nutshell, we can go to the properties of thermodynamic potentials, but before we do this, I would just like to present an alternative derivation of decrease in Gibbs free energy being equal to the non-PV type of work. I have done an alternative derivation for both dG as well as dA. I would like to remind you that since both of them are thermodynamic properties, so therefore, in whatever way we do the derivation, we are supposed to arrive at the same results, provided the initial and final states are the same. So, in this particular case, what I have done, I have started from the basic definitions, and I have defined du from the first law, and then at constant temperature and pressure, I find that dG is equals to the reversible work which can be performed by a system and minus the PdV work which is there, because PV work is anyhow in that particular case it is there. So, from here can you tell me that suppose I give you a statement, say that suppose a statement is given to you, say for example, I state that delta Gf, the Gibbs free energy of formation of water at say some particular condition, say delta Gf water at say 298.15 Kelvin and 1 bar pressure, this is equal to, say I tell you, it is equal to minus 237.1 kilojoules per mole. Can you tell me what this particular statement means? If I tell you delta Gf water is equal to at 298.15 Kelvin and 1 bar pressure equals to minus 237.1 kilojoules per mole. Well, this means that suppose we perform some particular reaction, say water, hydrogen at gas plus half O2 gas to give you H2O liquid, and for this particular condition hydrogen is at 1 bar pressure 298.15 Kelvin, oxygen is at 1 bar pressure 298.15 Kelvin, and the water formed is also at 1 bar pressure and 298.15 Kelvin. So, therefore, from this particular forward reaction we can actually get 237.1 kilojoules of energy we can get from here. It also means that if we have to decompose water into its constituents, we have to provide 237.1 kilojoules per mole of energy, provided the reaction takes place reversibly, right. So, therefore, the non-PV type of work in this particular case was the electrical work which has to be provided, or rather which is obtained in a galvanic cell where hydrogen and oxygen react to form water, or minus or this much amount of energy is necessary to decompose water to obtain its constituent elements. So, therefore, after this, in a nutshell, we would like to discuss the properties of the thermodynamic potentials. What are the properties of the thermodynamic potentials? We all of us know that all of them are the thermodynamic potentials are thermodynamic properties, and all of them are extensive properties. What does it mean? It means that U should be equal, it should be number of moles into the molar internal energy. Same way, the total enthalpy of the system is the number of moles into the molar enthalpy of the system. Your total Helmholtz free energy should be equal to the number of moles into the molar Helmholtz free energy of the system, and Gibbs free energy should be the number of moles times the molar Gibbs free energy of the system. And just like the total properties, here also we know that the molar Gibbs free energy is nothing but H minus Ts. In the same way, A would be equal to U minus Ts. Now, here I would very categorically like to mention something which you should be remembering throughout the entire course of phase equilibrium thermodynamics. Since we are dealing with a large number of properties here, so therefore, all total properties will be defined in terms of capital letters, and all molar properties will be defined in terms of small case letters. We would be maintaining this particular nomenclature throughout our class, or rather throughout this particular course on phase equilibrium thermodynamics. So, therefore, coming back to the properties of thermodynamic potentials, all of them are extensive thermodynamic properties. They decide the criteria of spontaneity of a process for different coupling between system and surroundings. I need not repeat. U decides the criteria for constant S and V, H for constant S and P, A for constant T and V, G for constant A for constant T and V, G for constant T and P. The other thing is it gives a measure of the useful work or the non-PV work to be specific, because we have found out that it is W non-PV minus PdV. So, therefore, it gives a measure of useful work a system can perform under given conditions of coupling with the surrounding medium. Well, the most important property of the thermodynamic potentials with which we will be primarily interested is that if you observe each and every of these particular properties, if you observe these the different particular equations, we find this was the combined first and second law that we have already discussed. From here we have come here. Just substituting A equals to U minus Ts, we get this equation. Substituting G equals to H minus Ts, we get this equation. So, for each thermodynamic potential, we have got one set of differential equations, number 1. Number 2 is we already know that all of them are properties of the system. So, therefore, they have exact, or rather they are exact differentials. What are the properties of exact differentials? If you remember, suppose P is an exact differential. So, therefore, in that particular case, suppose P is an exact differential and it is a function of say x y. Then in that case, I can write down dP is equal to del P del x at constant y dx plus del P del y at constant x dy. This can also be written down as m dx plus n dy, isn't it? And under that particular condition, I can also write down del m del y at constant x is equal to del n del x at constant y, because both of them are equal to del 2p del x del y. Since P is a property, so therefore, it hardly matters which differentiation I perform first. And based on this, all these terms have been differentiated, I have simply written down these properties in this particular form, and then I have performed this particular equality, and from here we get something which is very, very important, and we get a set of equations which are extremely important, and these equations are known as the Maxwell's equations. Just observe the Maxwell's equations. What do you get? You find that the Maxwell's equation, they give us the variation of entropy with pressure, the variation of entropy with temperature, with volume, with pressure, and these are related to the PVT properties of the different substances. So, therefore, we find from the differential equations of the different thermodynamic potentials, we come across a set of Maxwell's equations, and these Maxwell's equations are very, very important because they relate the non-measurable properties with the measurable properties. So, therefore, in the next class we are going to continue and find out how Maxwell's equations can be used to relate measurable with non-measurable properties. Thank you very much.